Today I'm going to talk about my work on understanding why and predicting when developers adhere to code quality standards. Static analysis tools are widely used in practice as they can detect bugs in programs without actually running them. Typically, companies like Microsoft have a suite of static analysis tools that analyze most of the code bases regularly to identify potential vulnerabilities and raise warnings that developers analyze to find out the true positive actionable ones that they must address. However, because of the high rate of false alarms, developers used to waste a lot of time in identifying the actionable warnings that they must address. And to solve this problem, existing research has developed many effective solutions that can accurately predict the true positive actionable warnings as well as the false alarms with high accuracy. Some of these solutions are very effective in practice as they can predict the warnings that must be brought to developers' attention with almost 90% accuracy. And with such high effectiveness, one would expect that developers would fix most of these actionable warnings because these are true positive warnings in real code. However, analyzing development teams' behavior on a single large code base at Microsoft, we found that the fix rate of these true positive warnings hovered over 45%, indicating that what developers and static analysis tools consider to be true positive differs. And this was the motivation for this study, whose goal is to understand when and why developers adhere to code quality standards, where we measure developers' adherence in terms of their actions to fix true positive static analysis warnings. And further, we want to predict developers' behavior based on this understanding. To achieve this goal, we first identify the factors to objectively measure true positive warnings from developers' perspective. And then we develop machine learning-based models that can predict developers' behavior based on the influencing factors. And finally, we provide some recommendations for static analysis tool designers on how they can make tools more useful in practice. Our key insight is to model developers' behavior of adhering to code quality standards using the fog behavior model that states that for a behavior to occur, the three elements, ability, motivation, and prompts, must converge at the same moment. As static analysis tools already raise timely alerts, we develop a methodology to objectively measure developers' ability and motivation for addressing the static analysis tools' warnings, and then we develop machine learning-based models to predict developers' behavior from their ability and motivation factors. Let me tell you more about our end-to-end methodology. So in step one, to identify the factors to objectively measure developers' ability and motivation, we first analyze how development teams use static analysis tools in their development workflow, the information stored about developers in the developer database, as well as the metadata stored about the code bases in the repository database. Based on this analysis, as well as the literature survey, we came up with 25 factors that can objectively measure developers' ability and motivation for adhering to code quality standards. For example, years of Microsoft experience denotes the number of years a developer has worked at Microsoft, measuring their ability to understand the importance of the code quality standard that is important for the company, as well as their ability to fix a static analysis warning that is raised within a given development context. Factors like is test code and is active code, they measure developers' motivation to address a static analysis warning that is raised within a given type of code base that developers are currently working on. Next, to understand when and why developers adhere to code quality standards using these identified factors, we define a code quality standard and extend a static analysis tool to detect both adherence and deviation from that standard. Currently, static analysis tools are designed to detect only bugs but not the fixes, which does not give us a complete picture of when developers did not introduce the bugs in the first place. Therefore, we propose to extend static analysis to also detect the scenarios or situations when developers follow the right practice. We perform a case study using Microsoft's band API standard, which teams at Microsoft are required to adhere to. The standard defines 337 APIs, which consist of 195 discouraged APIs and 142 their recommended replacements, which we call preferred APIs. We extended Serif Pattern Matcher, which is a static analysis tool solution, an open source solution by Microsoft, to detect both discouraged and preferred APIs with almost 95% accuracy. In the next step, we ran the Serif Pattern Matcher to scan almost 120,000 repositories and detect the use of banned APIs. We found that around 9,000 repositories use these APIs, which had C++-based source files. Now, to remove the noise from these 9,000 repositories, we selected the repositories that had at least 100 source files, 1,000 commits, more contributions from internal Microsoft developers, and were associated with the product or service that was under active development. This led to 162 repositories of interest that had contributions from over 15,000 developers, belonged to 15 diverse product teams, and had over 500,000 of banned API users, of which 84% were discouraged. So this gave us a good data set to understand this phenomenon. We annotated these 500,000 API users in 162 repositories with the 25 factors that we identified. And the table here shows the diversity of the factors in the annotated data set. As this is large real-world data, of course, we were not able to annotate all 500,000 APIs with all 25 factors because of either missing data or not having access to certain developer information prior to a given date. Nevertheless, our annotated dataset exhibited sufficient diversity to conduct our analysis. And so, in the next step, we identify which of these 25 factors influence developers' adherence to the banned API standard. And for this, we conducted statistical tests for each factor independently. Depending upon the type of the factor, for example, for categorical or dichotomous factors such as is test code or is active code, we use chi-square test of independence, while for numerical factors such as years of Microsoft experience, we use Mann-Whitney U-test to compute the correlation between that factor and developers' behavior to use preferred or discouraged APIs. Our analysis revealed that except for employee type and team size, all 23 of the 25 factors were statistically significantly correlated with developers' adherence to the banned API standard. For example, a weak positive correlation with years of Microsoft experience denoted that developers who have stayed longer at Microsoft are more likely to use preferred APIs, probably because they are more aware about the standard, while a negative correlation with author churn indicated that developers who modified their code more often were more likely to use discouraged APIs. Similarly, analyzing the distribution of the use of these APIs for factors such as is test code and is active code, we found that developers used more preferred APIs in the non-test code and the code that was under active development. Now that we know what factors mattered for adhering to the banned API standard, in the next step and the final step, we developed artificial neural network-based model to predict developers' behavior of adhering to the code quality standard using the correlated factors. Now, in the interest of time, I won't be able to explain the architecture of the model, and I invite you to read our paper. But the input to the model is a matrix where rows represent development context, which is defined in terms of the correlated factors. And the output is a two-dimensional vector that contains the probability of developer adhering to or deviating from the code quality standard. And based on those probabilities, we can identify what is the likely action that developers are going to take. We evaluated this model in two settings. So in the first setting, our training and test data set were split based on the code basis, such that the training data set represented one set of development teams and the test set represented another set of teams. We trained the model using a held-out evaluation data set to ensure that our model did not overfit the training set, and it took around 100 epochs to finish the training. On the test set, our model was able to predict developers' behavior with 92% accuracy. In the second setting, we created a new annotated data set by analyzing a single large code base for a period of 10 years at fixed time intervals and annotating the detected APIs with the correlated factors. We then split that data set at a fixed timestamp such that the training data set represented developers' past actions and the test set represented their future behavior. Similar to the previous setting, we used held out evaluation set to ensure that our model did not overfit the training set. And on the test set, our model was able to predict developers' future actions with 86% accuracy. Finally, based on these findings, we provide some recommendations for static analysis tool designers. For example, first, static analysis tools can use our factors to prioritize the warnings based on the development context. For example, we observed that developers addressed alerts raised on production code or the code under active development sooner than other contexts. Second, prioritize warnings based on the team's prior behavior and improve fix suggestions. So for example, if teams are not addressing warnings on a legacy code or a code that is external to that team, and instead implementing additional checks on the code that they are actively working on, static analysis tools can actually learn this and then improve the fix suggestions as well as prioritize the warnings on the external code accordingly. And third, improve warnings based on the developer's ability. So for example, for novice developers, static analysis tools can provide detailed explanation of the implications of the warning and how to actually fix it, or probably redirection to an expert developer who can help understand and address the warnings. Whereas for more expert developers, they can just provide the potential vulnerabilities and possible fix solutions. So to summarize our contributions in this study, we present a methodology of understanding when and why developers adhere to code quality standards and predict developers' behavior based on that understanding. And I showed you how we use our methodology to perform a case study using a Microsoft Band API standard and Serif pattern matcher static analysis tool. And finally, we provide some recommendations on how we can make static analysis tools more useful in practice by using our identified factors and models. With that, I'm up for questions. Thank you all for listening.
Thank you for your presentation. There is some question from the audience. Yeah, can you please come to one on the mic?
Hey Manish, this is Vibhu from Accenture Labs. I think the study is amazing, very useful as an area. I have one major doubt or maybe a comment about this. The band list that you do refer to, I would imagine that itself will evolve over time and has evolved over the last 10 years or so, right? So to apply the current version of this list to then cross-validate or validate or train over a past 10-year-old repository might not be the most correct way, right?
So, I mean, the Band API standard that we consider has been there since 2012, and it's, our annotated data set that we consider is the most latest version. Like this study was done like in 2021. For, regarding the factors that we come up, or the models, they are agnostic of the standard. So for example, if let's say there are more band APIs, the only thing that you will observe here is like, those are not detected in the data set, right? Those won't prevent the model's accuracy or prediction.
No, so why I believe they will, because there is a human factor involved, right? So if I do see something in the band list, I am obviously less, I would probably not use that, and if it's not a preferred one. When it does come in that list is important, because if I contributed to some code before that, when that actually came in, I'm not going to probably go back and change a 5-year-old code because something being addressed or identified in the band list now. So, and I think I see in your table, which is in the case study, that tenure in Microsoft actually correlates negatively with this. It's probably because those who have been there for long, they could go through code over time when those things are not in the band list and therefore were free to actually introduce this. Maybe, I mean.
Right, but we would expect the new developers to address those warnings, right? And what we observe, like again, this is anecdotal, is that instead of actually fixing that old code, what developers did was they implemented new checks in their new, like the code that they are actually working on, instead of addressing those. So they address those vulnerabilities using code reviews and implementing additional checks instead of actually replacing the banned API with the preferred one. And in some cases, it was actually a genuine reason which was related to performance, because so here banned is a misnomer. Actually, it's more like a discouraged.
Control list.
Yeah, exactly. So in some cases, they said like, we know that this is more performant. So even though static analysis tool keeps raising these erroneous alerts that you should replace this API, they say like, we know that it's not going to be exploited. So, yeah.
All right.
Thanks.
Thank you very much. There is another question. So I want to just ask you a curiosity regarding, so you mentioned static analysis tools at the beginning, so you develop your case standards that you apply in your model, no? My question is, did you have in mind to make some comparison between the other existing warning provided by different static analysis tools and try to combine them to detect the accuracy, or if, of course, they already mention and take in consideration the one that you develop?
Thank you for the question. So our work is kind of orthogonal or complements the accuracy-based work. So as I presented in the earlier part of my talk, like most of the research on static analysis has been to improve the accuracy of tools. And basically you're improving these rules that will detect these true positive actionable warnings. But then these existing work don't consider the human factors into account. So in that way, like, there's no like direct comparison of our accuracy with the accuracy of those existing tools. But what we would like to say here is, like, if you integrate our models and the factors in the existing research or existing tools whose focus is to improve accuracy, you're going to have a better tool that's going to be more useful in practice.
Yeah, but the problem is that, so I agree with you that the vast majority of the static analysis tools do not include the human factor. But the problem is that in my last paper, so we found that the static analysis tools has a precision very low, lower than 30%. So in this case, if you don't rely on the static analysis tools, it's better to try to identify if your model is complementary from the point of view that can substitute, let me use this term, and can provide much more advanced, because if you recommend to include the human factors to someone that has a defect to be not precise, maybe your model can suffer on some biases because you combine with something that is not so precise.
True. Yeah, I agree totally with you. Yeah, so if you apply this on a static analysis tool that is only 30% accurate, then we don't know.
Sometimes 18. So.
True. Yeah. But yeah.
Thank you very much again for your presentation.
Thank you.
Now we have the time of the third presenter, that she is online. So the title of the paper is Code Compliant Assessment as a Learning Problem. The presenter is Neela Sawant. So I hope that she already connected. So Neela, are you there?
Hi, can you hear me?
Yeah, we can hear you perfectly. Welcome. And the stage is yours.
Great, thank you. I am sharing my screen. I should see it momentarily, but please let me know if you don't. All right, great. Hi, everyone. My name is Neela, and I'm the lead author on this paper, which is a joint work with Srinivasan Sengamedu at AWS AI Amazon. This was done as part of Amazon's Code Guru service, which is a service to analyze your code using AI and finding the most expensive lines and buggy lines automatically. So let me start by defining the problem of code compliance assessment. It's always with respect to certain rules or best practices for software creation. And it can cover a range of topics, for example, security, concurrency, input validation, and so on. And the task of code compliance assessment is to verify that the code meets the desired behavior for the policy. And it can be really challenging. It requires deep expertise in program analysis, especially also because the natural language policy descriptions can be vague and may require a number of inferences to be made to verify a code. So here we illustrate it with an example policy. This is the description of CWE 197. And it states that truncation errors occur when a primitive is cast to a primitive of a smaller size and data is lost in conversion. And then you may be given a code snippet, right? And asked to verify if this is compliant or non-compliant. So in this particular example, the 2-byte array function takes 2 arguments. It takes an input and also a size. And then it basically compares the size with the integer maximum value, throws an exception if it does not meet the criteria. And if it meets the criteria, then it does the type conversion. So because it has met all these different criteria, the eventual assessment is that the code is compliant with respect to the policy. Now, as you can see, this is quite complex, and typically manual code reviews and static analysis, these are the traditional mechanisms for code compliance assessment. But the challenge is they are not always scalable, especially with growing number of programming construct, programming languages, different companies having their own custom documentation and own custom policies and so on. So we started out by a question, if we can auto-label a code as compliant or non-compliant or irrelevant using just a natural language policy input with machine learning. And this can help scale to policies not covered by manual code reviews or static analysis. And once you find some relevant codes, they can also use that to bootstrap your rule creation because they can serve as your test cases. We have looked at prior work on code compliance assessment, and there is some work in neural bug finding and code search, but we find that these tasks are not really studying large-scale analysis. So we refer you to our paper for the detailed survey, but in the interest of time, I'm just going to focus more on our contribution. So we developed a tool called Policy to Code. It's a machine learning based tool for code compliance assessment at scale. And it is founded on a representation learning framework where the policies and codes, their compliance relationships are maintained via the vector distances of their embeddings. So it uses a machine learning framework and proposes new machine learning tasks for pre-processing, pre-training, and fine-tuning using commonly available code and documentation datasets in public domain. And we have evaluated the system on real-world applications and benchmarks for 2 tasks for automated code compliance labeling and assisted rule creation. So I'm going to jump into the technical details now. So the first I will describe how we create training data sets. So machine learning models are data hungry. Unfortunately, for code compliance assessment, there are no really large-scale data sets that list policies along with their compliant and non-compliant examples. So we harvest such data set by repurposing and reinterpreting commonly available data sets such as code reviews, bug fixes, and documentation. We specifically looked at 150K GitHub code reviews and 32K bug fixes on GitHub and all of Java documentation. And we inferred policies and their compliant and non-compliant labels based on context. And we also sampled some additional negative examples by just randomly sampling unrelated documents or code examples. I will show an example of how we created one training example using a code review. So what you see on the screen is a code review snippet. So on the left, you have an original code, the generate password function. and it contains a line which creates an object of Java random class. And the reviewer has flagged this line and stated that it's probably better to use secure random for anything security related. And then the author went on to make that particular change. So we use this code review comment as a proxy for a natural language policy. And we engineer a basic prompt by combining that text with a compliant as prefix. And then with respect to this anchor prompt, we say that the original code is a non-compliant or negative example. And then the subsequent changed code is a positive example because it meets the criteria. So the definitions of negative and positives are anchored around the prompt. If we were to switch the prompt to using non-compliant as prefix, then the positive negative labels would be switched. That's just an important distinction I wanted to make. And of course, we can sample more negatives by sampling relevant codes. So once the training data is ready, then the main core of the work is about representation learning. So representation learning is the idea of learning embeddings. When you have a representation space or embedding space, the vector distances between the embeddings that basically naturally supports any kind of search operation. And you can also transform the distances using some functions like softmax to create a probability distribution, which is useful for classification purposes. So we start out by the triplets, like the anchor positive negative examples that we identified before, and we prepare them for machine learning. So we represent text and code as token sequences. For code, we use subword tokenization with byte pair encoding to prepare the input data. And then we pass them through an encoder, such as say CodeBird, which is also the core for policy to code, to generate embeddings. So now what this illustration is showing is on the left of the learning curve. This is the initial stage. You have all these circles representing your code and text examples in the vector embedding space, right? And the arrows indicate how far they are from each other. So right now in the beginning, the prompt is far away from the compliant example, but closer to non-compliant and irrelevant codes. And we want to optimize the embedding space such that the irrelevant and non-compliant codes are pushed away from the anchor and the compliant code is generated before. So this is executed by using a variation of triplet loss. So triplet loss, I've given the formulation, but essentially what it is trying to do is trying to compute the embedding FA for the anchor, FP for positive example, and FN for negative example. And it tries to compute a loss based on the relative distances so that the anchor positives are pushed closer together compared to anchor and negatives. So this is our fine-tuning process. To couple with the fine-tuning, we also use some pre-processing and pre-training schemes. So first, we only retain high-quality comments that resemble coding policies. Here we use doc2BP. It is a prior work published last year, and it tries to extract coding policies based on the natural language understanding of text. So it uses keywords and grammars and so on to identify what constitutes a policy. And we also use two tasks in a multi-task training setup. So the co-located documentation prediction, it takes code and text snippets and predict if they co-occur in a document. Then code comment matching task, basically given a code and a bunch of distractors, it tries to see which of the review comment correctly matches the code. And a similar setup, but by flipping the reviews and the code. So given a review comment, we can determine whether determine the correct code from the distractors. So we use all of these pre-training and pre-processing and fine-tuning setup. And then I'll come to the evaluation. So for evaluation, actually, we created a zero-shot benchmark from public domain datasets. So what is zero-shot? This is because we have policies and code in our datasets that are harvested from well-known benchmarks. So this is the first one is common weaknesses enumeration, and the second one is Code Guru's best practice test suite. And none of these policies and codes occur in our training data set because our training data set is at least, it's harvested from public, like other public data sets, and there's no intentional overlap. The policies we looked at, there is a classification whether they are specific policies in the sense that they contain actual programming, they name actual programming constructs and call out specific actions, or they can be highly conceptual. So we already saw one example in the introduction slide. And here is another example, which is very high level. It says thread management in a web application is forbidden and always highly error prone. So there is some little bit of ambiguity in the benchmarks, but we go ahead with it. And then we also add about 27K unlabeled codes from CodeSearchNet to set up a real world scenario. For baseline, we use CodeBot, which is a state-of-the-art tool for use for various tasks in machine learning for code. And then we also use it with a multi-class classification head, which is set up to do classification into compliant, non-compliant, or irrelevant labels. So these are classification and search are the two tasks that we evaluate. And for classification, we measure the performance in accuracy. And for search, we measure the performance in mean reciprocal rank. Okay. So after having covered the training and evaluation setup, I will jump into some of the results. So the first slide shows just how we tune policy to code. So this is purely about policy to code training. In the first table, we show the effect of losses and policy representation on classification accuracy. So basically, we tried a couple of different variations for triplet losses. There is a quadruplet loss and a batch multitask loss that we evaluated. And then for policy representation, we evaluated the prefix version, which is essentially some kind of like a basic prompt engineering, and another variation. But we found that this prefixed version, along with batch multitask triplet loss, that tends to perform better across the board. So we use that particular combination for subsequent training. So as you see, the performance is we always compare performance in terms of accuracy and search reciprocal rank, and we measure it on conceptual queries, specific CW queries, and CBP. Another note that I would like to call out is typically we see a lower performance on the conceptual queries and more like improved performance on specific queries. The CBP is actually a very highly curated data set, so it's got good ground truth and we see better results on it. CW, we noticed some issues with incomplete ground truth. So even if the examples were relevant, they were not marked as such. So the values that you see here, for example, in search MRR, these seem very low, but this actually is a lower bound on performance. And when we do some manual curation, we do see like the retrieved results at the higher ranks are actually useful. It's just that they are not marked correctly in the CW benchmark. So that's actually one of the open problem we consider later on. And then the second table shows the effect of pre-training and filtering schemes. So this is a ablation study that we did. Each row shows adding one type of pre-training task or a filtering task. And we see the classification and search comparison. What we do see eventually is how well all these different components nicely come together to improve the performance across all the data sets. Okay, and then the next slide is on baseline comparison. So we compared CodeBot, multi-class classifier based on CodeBot, and policy to code on the proposed benchmarks. And here we see that policy to code has a 53.84% accuracy on CW conceptual queries, way better than CodeBot and somewhat better than multi-class. And similar progression of seeing better performance on CW specific overall and CBP. And the search MRR also is significantly improved compared to the baselines. Finally, we conducted a user study to see how well policy to code can complement rule creation. So we used all the three techniques. We sampled 25 policies, and for each of the policies, using each of the approach, we chose we retrieved 5 compliant and non-compliant examples. This was done by setting up an Elasticsearch client over the 28K total examples, and the top 5 compliant, non-compliant examples were retrieved in a matter of milliseconds. So and so coming back to the slide, we then showed the policy and code pairs to 16 experts, which were like scientists and engineers at Amazon, and they provided their labels. We to ensure that there is no bias in the annotation, we randomized the order of in which the results were presented, and we masked the identity of the selection algorithm, as well as the actual labels and scores assigned by the algorithms to that particular pair. And this information was only used at the backend to reconcile all the annotations that we received from the experts. So here we see that for CodeBird overall, 7.2% of their examples were accepted. For multi-class classifier, overall 15.2% examples were accepted, and for policy code, 24% examples were accepted. And we see that the performance is little more for compliant than for non-compliant examples. So the takeaway from this particular analysis,
sorry Nila, okay, you have to conclude.
Yeah, is that we created policy to code as an attempt to scale code compliance assessment, but more improvement is needed to be of practical use. So we are trying to we can try to bootstrap compliance assessment for new and custom policies, but manual reviews, they are still necessary, potentially with some reduced effort. So in terms of validity, just like any other machine learning models, policy to code may also carry bias from training data set, especially if there are critical vulnerabilities which occur rarely. The training data sets may not be representative, and policy to code may also not recognize it properly. So in future, we are hoping to integrate with program analysis and domain knowledge, and do more work with ML and input transformation, such as prompt engineering, which is kind of taking off these days, and also improve our benchmark quality to make it more realistic and more accessible. So with that, I thank you for your attention, and I'll conclude my talk.
Thank you very much for your presentation. If there is some question from... No, there's some question from the audience. So I have one curiosity. When you, in the last slide, you mentioned in the trust validity that the critical vulnerabilities occur rarely. So in this case, the training data set might not be representative. So do you have considered taking consideration another data set? Because I agree with you that the model can check a lot of vulnerabilities, but important thing is to detect the ones that are considered much more critical. And for the criticality of vulnerability, I would like to know which level, so who decides, so are also based on the expert who are critical, or did you use a validated standard?
So if I understand the question, we want to know who decides what is critical and how to provide data for that.
So no, I'm just curious on the fact that you say that in threats to validity, you cannot represent the critical ones. So I would like to know if you have already in mind how to solve this problem.
All right. No, I think certainly an open question. So this is coming more from the observation that we see better results for common problems like versus something like security vulnerabilities, etc. They rarely occur. And so if we break down the results by these categories, we find that the performance is lower. So I guess what would be important is to be aware where the model can break and provide more control to the humans to provide feedback and provide more examples on the fly that it can take into consideration and improve the model iterative. So human in the loop for ML, I think that's where we are kind of heading, but it's right now the assessment is purely anecdotal.
Okay, thank you very much, and thank you again for your presentation.
Thank you so much.
Bye. So now is the time for the next presenter. The paper is an empirical study on quality issues of deep learning platform, and the presenter is here on the stage, Hongyu Zhang. So.
Yeah, thank you very much. Yeah, my name is Hongyu, and this work is mainly done in Microsoft Research Asia. Yeah. So we all know that nowadays there are many deep learning platforms like Google Cloud for AI, NVIDIA Cloud AI, and so on. So these cloud platforms provide deep learning service for many developers. So developers could submit their jobs to the deep learning platforms, and then the deep learning platforms will schedule the jobs and execute the jobs. Yeah, so Microsoft also developed its own deep learning platforms. So in this paper, we call it Platform X, which is not a real name, just for some confidential purpose. So this Platform X is similar to many other deep learning platforms. So basically, it utilizes many hardware, like a CPU, GPU, and so on. It also utilizes Kubernetes for job scheduling. Also, it applies many storage service. And on top of it, there are many deep learning frameworks like PyTorch, TensorFlow, and so on. And the user could access those deep learning frameworks. So as I said, many developers could submit their jobs, and this deep learning platform will schedule all those jobs and allocate the jobs to the GPU resources, and the data are stored in the distributed storage. Okay, so you can understand that the quality of these deep learning platforms is very important, right? Because a lot of mission-critical deep learning jobs are running on top of these deep learning platforms. Therefore, the quality of these deep learning platforms is very important. So we actually found that there are a lot of their jobs still suffer from many quality issues. So we conducted one of the first empirical studies on the quality issues of deep learning platform. So we studied actually 360 real-world quality issues. We analyzed the symptoms, the root causes, and try to understand the quality issues of this deep learning platform. In particular, the Platform X in Microsoft. And we also suggest some possible research work in the future. Okay, so for this work, we collected 360 real-world issues from this Platform X during the 4-month period. So we actually look at the issue title, we look at the bug reports, we look at the discussions, and we also look at the root cause and so on, the fixed solution and so on. We try to understand better the quality issues. If we are not very sure about a certain issue, then we just turn to the site reliability engineers or even the job submitter for details. So we found that there are some common symptoms for deep learning platform issues. For example, almost all the common symptoms, about 92.5%, are related to the specific deep learning jobs. The largest category is about the job crash, which is about 55% of the total failures, total quality issues. Okay, we also try to understand the root cause of the deep learning platforms' quality issues. So we found that there are 3 dimensions of these issues, like hardware faults, like platform side faults, like user side faults. Yeah. So basically, there are many issues which can be categorized into 3 dimensions: hardware, platform, and user. So I will go through each of them one by one. So for hardware issues, we found that it accounts for nearly 1/3 of all the common causes. So these issues may be caused by the failures of GPU, the failures of network, and the failures of computing nodes. Yeah, for example, GPU memory faults, NVLink error, and so on. Yeah, so actually this slide shows an example of the NVLink error. You can see that we actually look at this error message, this log message, and we found that there was a CUDA error. Yeah, it says that there was an uncorrectable NVLink error. Yeah, NVLink is the direct GPU to GPU communication tool. So we found that there are some NVLink problems. So there are also many other errors. For example, network-related errors, InfiniBand problems, and also the failures of computing nodes. Yeah, the server, the hard disk may fail, which causes the problem. Okay, so there are also many platform-related faults. Yeah, for example, some faults, these platform faults actually account for nearly 1/3 of all the common causes of the quality issues. And the system defect, resource overload, and the platform maintenance are the top 3 categories. System defect is the largest category and costs about 37 quality issues, which is about 10.28%. So I'll give some examples about platform-related faults, like system code-related bugs. Yeah. Sometimes the platform forgot to package a dependent library into the Docker image, which cause problems. There are also service misconfiguration problems. Yeah, for example, a deep learning job failed due to a misconfiguration. Yeah. And also there are some resource overload problem because many people are competing the deep learning resource. So there are resource overloading problem. Yeah, for certain system resource, the platform does not have explicit quota control. Therefore, the user does not know that he has already overused the resource that is allocated to him. Therefore, it may cause some resource overloading problem. Okay, so we also found that there are many user-related faults. Yeah, some problems are actually caused by the developer, by the end user. So they submit buggy code to the platform, which may crash after some time of running. So in this case, a lot of GPU resource and time are wasted. Yeah, therefore, we need to look into these problems. The buggy code, the policy violation, and the improper permissions are the top 3 out of 5 categories. Okay, so this is an example of a buggy code. Yeah, so the user upload the job, but actually the file cannot be found. So maybe this problem could happen after 1 hour of execution, 1 hour of training, right? So in this case, a lot of GPU resource and time were wasted. Okay, so there are also possible research work to deal with the quality issue of deep learning platforms. So from our study, we found that a lot of nodes could fail, right? So it's possible that we could develop a defect prediction model to train a model to predict which hardware device, which computing node, which GPU may fail in the near future. Therefore, we need to prevent to allocate jobs to those nodes, to those GPUs. Also, we could develop a tool to analyze the program hang. Yeah, we could develop static and dynamic hang analyzer to reduce this type of issue before the job is submitted. Similarly, we could develop a tool, static tool, checking tool, to detect various quality problems in users' code, to make sure that the code is actually working before the code is submitted to the DR platform. We can check the program, check the scripts, and so on. So we could also do fault-aware job scheduling. Yeah, we know that some computing nodes may fail, some GPUs may fail. Then we could do a kind of scheduling, right? Better scheduling to schedule the jobs to those nodes that are unlikely to fail in the near future. Yeah. And we could also do some testing, more extensive testing, stress testing, model checking, to test the quality of the DR platforms. Okay, so that's all about this work. So basically, we conducted one of the first empirical studies on quality issues of production DR platform. So we identify common symptoms, root causes, and so on. And we also suggest possible future work based on our findings. Okay, yeah, thank you very much.
So, okay, perfect. Thank you.
Thanks for the cool talks. One question, maybe a curiosity. It seems to me that the different type of faults that you found are typical to any distributed system, right? Like, were there anything deep learning specific that you observe?
Yes, there are some deep learning specific, like GPU errors, right? The GPU errors. GPU errors and also NV link problems, infinite band problems. Those are node outages. So basically, all those are kind of deep learning specific, like GPU unavailability, DPU driver problem, NV link problem, infinite band problem.
Okay. But it could be any other type of machine learning workloads, not necessarily deep learning. Like even if I'm doing reinforcement learning, I could experience some of those.
Right. If you also use GPUs and so on.
Okay. Thanks.
Yeah. Thank you.
Thank you very much for your presentation. Other questions from the audience? No? So thank you very much.
Thank you.
And good flight to come back. Okay, so now is the time of the first journal first of our session. Title is Can Static Analysis Tools Find More Defects? A qualitative study on design rule violation found by code review. The presenter is Sahar Mehrpour. Sorry for my pronunciation. The stage is yours. You have 7 minutes in total.
Thank you. Hello, everyone. I'm Sahar Mehrpour from George Mason University, and I would like to present my paper today. So first, I would like to talk about defects. What is a defect? There are different definitions for defects. Some consider defects as any piece of code that leads to a system failure. For example, in publish-subscribe design architecture, if an event is thrown before anything is registered for that, a defect may occur. Another definition for defects can be a piece of code that reduces the quality of the code. For example, if in a code base there are logger functions and a developer instead uses printing, a defect occurs. So in this paper, we are using a broad definition of a defect in which any piece of code that a code reviewer considers as wrong is defect. So how these defects are detected? Developers are primarily rely on code review to detect defects. However, the problem is that code review is a tedious task and is time-consuming. So developers are encouraged to use tools to detect defects and fix them before submitting for code review. And in this paper, we are focusing on static analysis tools, and we are considering them and investigating to see how well they can perform in detecting defects. So when we look at prior work, we realize that prior work actually examined individual tools to detect defects and seeing how they perform detecting known defects. And there is no study that see and examine the potential of different types of static analysis tools to find defects. And specifically, we're looking to answer these questions. We're looking to see how many defects can be potentially detected by static analysis tools, and what features should be added to these tools to detect more defects. So to answer these questions, we collected more than 1,300 review comments from public GitHub repositories. And we examined the defects found in these review comments and mapped them to the violation of rules. And some of these rules can be checked by static analysis tools. So we actually founded static analysis tools by matching the characteristics of static analysis tools to the defects in our data set. And from that, we could create a taxonomy of static analysis tools with 12 classes. So for example, we found one type of class is AST pattern checkers, which are tools that check rules that are expressed as AST patterns. Another example of these classes is style checkers, and these tools actually check rules related to code style conventions. So you can learn about our taxonomy and other classes in the taxonomy in our paper. So we actually annotated the defects in our data set using this taxonomy, and we found that more than 76% of the defects in our data set could be potentially detected by static analysis tools, which is a great number. We also found that more than half of these defects can be detected by AST pattern checkers and style checkers. Again, this shows the applicability of these sorts of tools. And we found that among the defects that are not detectable by static analysis tools, there are mainly maintainability defects and implementation defects. So next, we wanted to see how can we reach to these numbers and what features should be added to find these 76% of defects. So we actually look at the defects and examine them individually. And we found that there are many project-specific rules among the defects in our data set. So one obvious feature would be tools should be extended to support configuring and checking project-specific rules. Another observation that we had was related to AST pattern checkers. And we found that AST pattern checkers should be extended to support cross-cutting rules, which are rules that are affecting multiple files and modules. And finally, another observation that we had was about style checkers. So style checkers should be also extended, and actually they require to have complex parsers and apply dynamic analysis to check even more complex rules. So there are actually more findings in this area, so you can find them in our paper. So in summary, we actually studied the potential of static analysis tools to detect more defects. And we found that static analysis tools has a great potential. They can detect many defects in code review. And we also found that there are many project-specific rules, and these sorts of defects and rules are very important to actually be found in code bases. And we also found that AST pattern checkers and style checkers are the most applicable types of static analysis tools. They can detect as many as half of the defects in code reviews. And finally, the defects that could not be detected by static analysis tools may require human judgment to be detected. What it means that they cannot be formalized, and tools using information like identifiers, comments, or developers' knowledge can be used to detect them. For example, consider a rule in which developers are required to add comments to a complex block of code. And these sorts of information can help the tools to identify what piece of code is considered as complex. So thank you for your attention, and please read more about our paper and finding in our paper. Thank you.
Thank you very much for your presentation. Question from the audience? Yeah, Paula.
Just a question about, static analysis tools have a formal basis, no?
That's right.
You know already what they are going to capture and what not. So, what you did is, in the set of potential defects that a static analysis can get, you could devise should use very much. Okay, very shortly. So static analysis tools are formally defined. So you know already which kind of defects they can detect or not. It's by definition. I mean, it's not clear to me. What do you mean when you say the set of defects that potentially the static analysis can detect? It's not clear to me what does it mean exactly.
Yeah. So good question. So if you look at like individual static analysis tools, each of them detect like a subset of defects. For example, the defects that can be found by PMD are not the same as the defects found by findbugs or error-prone or other sorts of static analysis tools. Each of them like have different technical abilities. So here we are looking to see like we are looking at static analysis tools as like a class of tools. We are not looking at individual tools to see which defects they can find or they cannot find. So this is our purpose. We want to see the potential. If you gather all the static analysis tools and if you improve them to their extent, how many defects can you find with them? So that was our purpose.
Thank you very much for your presentation. Now is the turn of the second journal first. DebtFree, minimizing labeling costs in self-admitted technical debt identification using semi-supervised learning. The presenter is Tim Menzies. It's here on the stage.
So I have to warn you that I am cursed I'm trying to get to if I can get some technical help. If you can get me to, he's gone to the proceedings and he's found the link to my slides and he's trying to get that up. And this is, I believe, the last talk of ICSE. So this will be a short talk. I don't think we have 10 minutes fully. And I'm just asking now, did you find the... Oh, I'm not the last, okay. So I'm trying to find my slides, which I can get to if I can get to a web browser. Or, yet again, I will do a cappella my presentation, which is the third time this meeting that my slides have failed. So who's the tech person? Can they wave their hand, please? Okay. All right, let's forget the slides and let's see if I can do this a cappella. Very good. So this talk is about technical debt. Technical debt is the dust in the machine that collects. As we develop code, we make shortcuts and we leave comments like, "This is crap, really have to fix this up later on." Technical debt is like the dust that collects in the cogs and slows things up. The recent research on return on investment of fixing technical debt is very, very supportive of the idea that if we found technical debt and fixed it, we have dramatic effects on the maintainability and usability of the code. The slides in front of you show examples of technical debt, and they're comments where you can absolutely see developers have committed code that contains statements like, "I'm not really happy with this bit, but we're going to commit it right now, and that's going to be the end of it, and we'll just carry on from there." And if we all put our hands on our heart, we all know that we have rushed out code that perhaps wasn't the best, and we're just going to fix it up from there. Now, about 3 years ago, one of my students, Yuriy, who's now at Rochester, he was doing some reproducibility studies on prior technical debts, and he found an interesting quirk in prior work on technical debt. People would report a recall of detecting comments that trigger technical debt, and that recall was around about 70–80%. And he pointed out that really there was a bimodal distribution, that in the problems he was seeing, there was actually a very easy group of comments to see they were technical debt with very large recall, I hope you're all impressed about this, by the way. No slides at all. Okay. Thank you, thank you, thank you. There was a group with a very large technical debt mess up, and a group with a smaller group where the recall was not 98%, it was terrible, terrible. So he found this second smaller group of technical debt problems with disastrous properties. So he wrote something called jitterbug, which, as you know, is a two-step dance. And step one handled the very easy cases of doing technical debt with very, very simple methods, very simple classification schemes. And when he got to the second step, the hard step, he brought out the big guns, active learning methods, where humans and classifiers would go into a loop. And the active learner would say, I think based on what I've seen before that that's a problem. And the human says, no, that's not. And the learner would adjust itself. And then you keep going until the active learner keeps fetching things that are actually a problem. And with that, Yuriy had a TSE paper which achieved very high levels of technical debt because it had different methods for the very hard and very easy. But the problem with jitterbug and Yuriy stuff is that it required labels of the data. And those of you who've worked with real-world data know there's a ground truth problem, actually finding these labels. And every time we've picked up data sets and looked at the labels and double-checked them, we have found that we do not approve of the labels. In fact, I would say that bad labels are the great secret, the Titanic of modern analytics. Most labels we get are bad. And so Ken, who's Hugh Chu, said, well, can I do jitterbug without labels? Now, at the same time, we were learning about unsupervised learning, J.C. Nam's CLAR tool. And what CLAR does is it takes all the numeric ranges for the data set, divides them at the median point, and it has the heuristic that if you're large, you're probably bad. Larger methods are probably defective. Methods with too many variables are probably defective, etc., etc., etc. And so what CLAR would do is he would take a new instance and ask on how many times are the numbers of these independent variables above the median point, count it up, and after a certain threshold, he declares defective. Notice that's an unsupervised learning method. It's just reflecting upon the independent variables. And he achieved success with that, and that was reported at FSE 15. And so the paper in front of you is a combination of J.C. Nam's CLAR algorithm and Yuriy's jitterbug algorithm. And here's the thing I want you to remember. When Hugh did this, when Ken did this, he found he only needed to have 1% of the data labeled. So we often talk about the complexity of data quality. And it turns out that data that's from software engineering projects has repeated structures. We often write things the same way multiple times. People learn structures from the same books. A lot of software engineering data has repeated structures. If you've got repeated structures, that means you can replace many examples with a smaller number of exemplars. And this is actually the semi-supervised learning manifold assumption. The manifold assumption is most data mining works really because underneath the high dimensional data we're looking at is a lower dimensional manifold, and the high dimensional data can be approximated by the lower dimensional manifold without much loss of signal. Semi-supervised learning is called the quiet revolution. It's a statement that we don't need most data, that we can actually throw away most of our buggy data. Semi-supervised learning is this great secret on how you can handle vast amounts of low-quality data. And when Ken tried it in this particular example, we have a whole paper at MZ that shows that with just 1% of the data, we could tune some of the magic parameters in CLAR, and we could achieve what Yuriy did with lots of labels with very few labels, and thereby we could identify the technical debt comments. And I think I should stop there. I think that's about as much as I can do with the materials in front of me. Thank you very much. Any questions or comments?
Thank you. Question from the audience?
If any smart ass asks about the typo on slide 7, well, we'll just send them out of the room.
Before I go up. So the hard to label ones, right? You said the easy ones are very easy, and then the hard to label that you do with active learning. Did you look if they correlate with also more complex type of technical debt? Like
Oh yeah, sure. I mean, the hard to label ones are the more complex problems. And what Yuriy was reporting is that literally dozens of prior articles were reporting very good results because there was this, but because they just didn't pick up on this very hard group.
Because they're also more infrequent, maybe.
No, I don't think, I think he did a little bit of smoting. I don't think it was an imbalance problem. It was actually a class, I think it was like 20%. Yeah, I think it was actually 20% was the hards. Yeah.
So thank you very much, team.
Okay.
So now is the time of another journal first. Title is Fix Me, synchronized with the database and empirical study on data sets, self-admitted technical debt. Presenters is Fotsika, so the stage is yours. 5 minutes of presentation plus 2 of questions.
Oh, 5, okay. How do we do the slide next? I don't know. You just there? Okay. Anyway, so thanks for attending the talk. So this is actually the work of my PhD students who couldn't make it. Then I have to present. But he's the one who did all the work. Okay, great. So the work is about self-admitted technical debt. What we're focusing in this work, it's a specific type of debt in data-intensive systems, right? So there have been a lot of work looking at technical debt in traditional systems. At the time when this work was ongoing, we realized that very little attention was given to data-intensive systems. So what are data-intensive systems? What basically is they are systems for which a big part of the logic is interacting with data, like getting access to a large volume of data and processing this data in a more efficient ways. And this part of the implementation logic that access and process data also happen to experience a lot of technical depths, and we wanted to characterize this to make it more explicit and build a taxonomy out of this. So what we did in this work was actually trying to look at both NoSQL and SQL type of systems, looking at the part of the logic that is responsible for fetching and processing the data, and try to understand what kind of depths are more frequent in that part of the code, and complement existing taxonomy of self-admitted technical debt that have been proposed for traditional software systems. Yep, so, and we focus mostly on data access classes, and also we look at non-data access classes, and then we compare the dynamics. So it's typically an empirical studies around. So this is an example of technical debt in this type of systems. So this is a self-admitted one, so the developer usually puts a note acknowledging the fact that the implementation is suboptimal, and then that they intend to come back and fix it and implement it. So, and improve it. So we wanted to see what are the different type of these issues and what are the more common ones, what are the more frequent ones. So these were the research questions. What is the diffusion of self-admitted technical debt in data-intensive systems? We also wanted to understand how they evolve over time. We wanted to understand how they are composed. So what's the nature of this type of debt? What's the typical structure for this type of debt? And in the 4th questions, we look at the circumstances behind their introductions. Like what's usually the root cause for the introduction of this type of debt in the systems, and eventually when they are removed, if they happen to be removed, how are they removed and why they are removed? So we collected data. So we went to GitHub, as most of these type of studies. We look at systems, data-intensive systems, both relying on SQL and NoSQL type of systems, and then we track the evolution. We collect the evolution history of the systems. We built a detector, which is NLP-driven, so we could catch the different spaces in the code where the developer marked the existence of the debt. So we collect all those depths. Then we did manual labeling with card sorting, multiple evaluators to kind of classify the different type of depths across the different categories, removing duplicates and building a taxonomy. And using the collected data, we actually went on and answered the different research questions. So the first question was about the diffusion. So we wanted to know the prevalence of this type of problems and where they are more prevalent in the systems, contrasting SQL and NoSQL systems, and over time. So as you can see on the results, data access self-admitted technical debt are less prevalent than regular self-admitted technical debt. I think this is a bit expected also because they represent a smaller part of the logic of the systems, which, although it's a more important part of the system because they are heavily data-driven systems. They have a tendency to grow as the system evolves, so this is an interesting observation. So maintenance of this part of the code is actually critical. NoSQL systems have higher median data access self-admitted technical debt, so it's more prevalent in NoSQL systems than SQL systems from this observation. We also look at the survival, so how long they stick into the system before they're being removed. And what you observe, you can see on the slide, is that data access self-admitted technical debt, they have lower survivability probability. So they are removed pretty much a bit faster than the non-data access, self-admitted technical debt. We contrast for SQL and NoSQL, and then you can see that data access self-admitted technical debt, they have lower probability in both SQL-based and NoSQL-based systems, so the similar trend across. And what was one of the core contributions of the paper is actually this taxonomy. So we augment the existing taxonomy of self-admitted technical debt that have been published in the literature a few years before, adding all those that you see with the data mark, the new type of self-admitted technical debt that we found to be specific to the data processing part of the systems. So the most frequent one was the type of technical debt related to low internal quality depth of the codes. And we found that most of the data access self-admitted technical debt, they have higher prevalence in SQL systems. With this, we wanted to try to understand the dynamic of the introduction and removal from the systems. And we found that they are usually introduced much more early on in NoSQL systems compared to SQL-based systems. They are removed late. We found only 12 cases of removal across all the systems that we process. So it's removal of this type of debt seems to be quite infrequent, which is a concern. And usually it's happened during bug fixing and refactoring. So those were the main reason behind the introductions of this self-admitted technical debt in the system, followed by feature enhancements and the request for new features. Data access debt removal commits, they are often associated with feature enhancements and bug fixing. So we didn't observe any explicit refactoring operation. So most of the removal that happened were accidental, either the feature went away or the part of the codes that were implementing the debt were refactored and improved or evolved. So key points from this, most of the detail are in the paper. I strongly encourage you to fetch the paper and read the paper. So technical debt is a rising subject in systems. Higher priority should be given to them, so I'm advocating for this. And they are prevalent in data-intensive systems. They have a bit lower prevalence compared to traditional self-admitted technical debt, but they are a significant part of the debt that crippling the system over time, and they tend to increase, the density tends to increase over time as the system evolves. There needs to be more focused refactoring activities to remove this type of debt to the system, and we observe that the removal currently from the system that we have studied, it's mostly accidental. So they don't seem to be prioritized. So that was it. So I wanted to talk to you about self-admitted technical debt in data-intensive systems, and how they evolve in the systems, and this taxonomy that we have proposed to characterize them so that they can be better managed and maintained over time. Thank you for your attention.
Thank you very much for your presentation. Question from the audience? So I have a small question. So
Sure.
Did you have in mind for the future where to consider also possible correlation with the no self-admitted technical debt, so the technical debt detected by some static analysis tools?
Yes, it's actually ongoing. So yes, definitely.
Perfect.
So we plan to expand beyond this.
Okay, thank you very much. That's it.
Thank you.
So it's the time of the last presenters. So the paper is how does quality deviate in a stable releases by backporting. So the presenter is Yuriy Tasmin. So please, the stage is yours. 5 minutes for presentation and a couple of minutes for questions.
Sorry. Hello everyone, I'm Zareen and I'm presenting my paper, How Codebase Evolve in Stable Release Maintenance. So, okay, it has been proven by existing literature that maintenance costs actually cost more than developing a new one. And maintaining the stable releases actually takes up almost 35% of existing maintenance cost. And this thing is actually supported in industrial setting by backporting. So why are we maintaining existing stable releases, like multiple releases? What happens is, let's take an use case scenario. Python 2 came in the year 2000 and Python 3 came with extended features in 2008. But even after Python 2 was backdated, the authority had to ensure maintenance support for Python 2 for 12 long years because there has been existing demands. So Python is not the only case. This type of long-term maintenance support is also ensured in the industrial setting for multiple systems and frameworks and libraries like Linux, Django, Chromium. So what happens actually in backporting is when a bug occurs in the upstream developments, they actually provide support for the bug for the latest release. But when for the previous stable releases, they actually propagate the similar change or a slightly modified change version to the preceding release to fix the existing bug, the same bug to the previous release. This is an example of backport pull request in Elasticsearch project. Okay, so why we are talking about backporting? How is it different from other pull requests? The existing literature have already found out that backporting often offered separate time and attention in its life cycle, and also the pragmatic procedure to constitute a backport is slightly different in industrial setting than forward porting pull request. They are not always inspected and reviewed in a constant manner that is done in normal pull request scenario, and also an explorative analysis on backporting have found out that almost 50% of backports have to accept 13% of mutation changes on top of original pull request to support the identical fix in the previous releases. And also the strategies, security concerns, and challenges that are encountered in backporting are significantly different than forward porting pull request scenario. So in this study, we are trying to find out that all these aspects backporting are different, how code base actually enlarge, how code base expand in a stable release maintenance scenario, and also we will try to find out whether the changes that we are introducing in backports, whether they are actually, they can make the stable release vulnerable or not. So at first, we actually retrieved 1,000 repositories from GitHub, and then we put up some inclusion and exclusion criteria because we wanted our dataset to reflect the real life projects. And then we ended up with 263 projects. For this study, we took only 3 projects that have highest, 2 with highest forward porting and back porting ratio, and 1 SALT, which is with lowest forward porting and back porting ratio. Then we actually mined the changes each stable releases have accepted by this, in this subject system by backport history miner. So we actually, for each aspect where the subject system has changed, we actually decided, we actually sorted out some matrices for size, complexity, and coupling, and then we actually mined the micro-level artifact evaluation. What we did is for each file that have gone through the chronological order of the commit, we actually tried to find the matrix value on each commit that each file accepts after the repository has been released, and then convert it into a regression line to depict the file evolution. So we can see that one single file in a.py, the complexity aspects of this file has encountered different evolution in different releases. This is the distribution of tagged regression slope. We can see that gradual changes and outlier quality degradation is also visible for multiple projects. If you are interested, you can take a look of the paper. So while disclosing the vulnerability aspects of a backporting pull request scenario, we used safety library to identify third-party vulnerabilities, and in this way we identified 42 in Ansible, 37 in Kibana, and 7 in Salt. And we also used Shelltext library to find out lexical vulnerabilities in Ansible, and in this way we found out 21 vulnerabilities in Ansible. So when vulnerability occurs, sometimes the library can be different. Like the library that is kind of deprecated in today's context can be used like in the previous context. So we also mapped the time frame with Python CVE dataset, and then we used a correlation analysis to find out whether this quality degradation and vulnerability occurrence are correlated or not. And we found out that for Ansible's subject system, it's actually significantly correlated with 5% confidence interval, which actually tells us that we should look into it in broader scope. So in future, we would like to make a broad, we want to work on a broader scope so that we can identify the vulnerabilities and also the weak changes that we are propagating to our stable releases, how these changes are actually affected by strategies, and whether this kind of changes that we are incorporating in backports are making stable code structures smelly or not. So thank you.
Thank you very much for the presentation. So there are questions from the audience.
Any questions? No? Okay.
Okay, so I think so that we are run out of the time, so we are extremely all late, sorry.
Oh, it's okay.
Thank you very much for attending one of the last one. Thank you very much.
So while our colleagues file in, I just want to say a few thanks. One is to the speakers. When something goes wrong with their presentation, it won't present, or it can't be found, or something's not quite coordinated, it's quite challenging to speak in front of a large audience when things are not quite right. I want to thank the MCEC staff, not just the technical staff here, but also all the venue staff that put on our food and made a beautiful venue for us and handled all these kind of issues going on when someone forgot to put their presentation up, or it's got a different name, or it just won't work. It's super, super challenging to run such a large conference in such a complex venue, such a large number of people with different kind of technologies and so on. So thanks so much to them. And also the session chairs. So I've been in a few sessions now where the session chair has to really, when you've got 9 or sometimes 10 items and there's a slightly not quite right working thing there, it is very challenging for those session chairs. I think they've done a fantastic job. So for those 3 groups of people, please give them a hand. I think. my acknowledgement of country, so somehow this got lost on my first slide and I had to ad-lib it. So I'm actually going to say it from the heart now. So I acknowledge the traditional owners of Nam, that's Melbourne, the Brun Yarra River, which is outside there. So they're the Wurundjeri Woiwurrung people of the Kulin Nation. Pay my respects to elders past, present, and emerging. And also to all elders of all First Nations communities that visit our wonderful convention centre and Nam. And I also recognise the significance of the Brun to the traditional owners, the life source and a meeting place. Seek to honour over 40,000 year tradition of building community, exchanging ideas, creating technologies to live in this challenging environment. And also whose sovereignty has never actually been ceded by the traditional custodians. It's still actually their land. So we've had almost 1,000 separate presentations, give or take, with keynotes and panels and breakouts and so on. Almost 100 main conference sessions in the last 3 days. 180, I think I counted up, and I lost count after about 170 something, so that's somewhere around 180, give or take. Co-located event, workshop sessions, and there's of course a few tomorrow as well, of course. And the last count, when I ran the report yesterday, I meant to run it this morning because I think one or two more crept in, there's about 1457 or something. That's head count. So of course a number of you have attended multiple things and so on. I think it mostly went pretty well. That's my hope anyway. Maybe I'm being slightly optimistic and so on, but I think the feedback I've got's been tremendous, so that's been really great. There's some certificates. I think most of you have got things that we handed out at various things, but there's some to people who weren't present we'll send out. I want to give one to all the organising committee members, but you'll get an electronic one. Same as the student volunteers, anyone I've forgotten. And hopefully we managed to present everything else at one stage or other during the conference. Actually, organising the award presentations turned out to be more complex than I envisaged, and Laurie and Max and I think, where are we going to put these in the program? How do we do justice to some of these and so on? So that's actually getting a bit challenging when this, of course, is our major community event, and we want to acknowledge all those wonderful contributions people have made in various ways, and fitting it in the conference is actually a little bit of a challenge, but hopefully we did okay. Special thanks to the ICSMA, who, I forget the acronym, what it stands for, sorry, who ran the ICSE week. So Kate's the team lead. Jess did a huge amount of work in venue coordination and so on. Emily, you would have, probably all of you got emails from at some stage at registration, and Andrea, the sponsorship, Tiffany, the exhibition and so on. And there's been some other ICSMA team members as well from time to time. So big thank you to them, please, as well. I forget the number, 50-ish, something like that, student volunteers. So they did a whole bunch of different things at different times to help run things. Some of the work they had to do was more challenging than others, but I think they've been super helpful, super enthusiastic. Most of them are students early to mid of their journey as researchers. And I hope they got a good sense of going to sometimes sessions they never would have gone to if they'd chosen the title and so on. Some kind of ideas that are going on in this very broad community that we have in software engineering. But also I think a number of them that I've talked to suddenly have been inspired, thinking while they were listening to talks, hey, my work is as good as this. I can submit to ICSE or an ICSE co-located event. And I hope to see, in fact, lots of their submissions in years to come. So another big thank you to them, please. The organising team is enormous. The 70-odd people that helped run the ICSE main conference bit, but there's also nearly 100 co-located and workshop chairs, program chairs, various other organising committee members that then bulled it up to 200, 250 or so. And then our reviewers. So I think Max gave you an idea about the volume. We can run an ICSE conference just with our reviews, let alone anything else. So that's a tremendous amount of work. It's all unpaid. it's all volunteer work. No one got paid for any of this. They did it as part of, I mean, you might claim it's part of their job, but they could have done other things like write their own papers. So that's all volunteer work. And so this conference and all our other conferences and journals would not run without that peer effort that goes into it. So again, I think that's just an amazing thing to do. The sponsors will make a profit. Might be not a massive profit, but it's certainly a respectable one. And we've been able to do a number of things. I hope you enjoyed some of the things with the animals and the kind of cool party stuff and so on. Some of those things were not that cheap. And our sponsors enabled us to do some of those things that I hope you enjoyed, hope you got some enjoyment out of and help facilitate the kind of conferencing and so on. So I really do thank all our sponsors very deeply. And again, ultimately, what's a conference without people presenting, people writing the papers, and people turning up to listen? So give yourselves a big thank you. That is just about the last thing I have to do. So now we're going to have a little presentation from our 2024 general chairs. Please come up. Wow us with the rah-rah for Portugal and more or less hand over. Thank you. Green button to forward.
Okay, hello everyone. So as you might be well aware by now, so next year's ICSE will be in Lisbon, Portugal. Okay. We, myself and Anna, we are the general chairs, and Peggy, I guess she's somewhere here, over there, and Abik, they are the program chairs. By now, of course, and we will see that there are some things already happening, but all the information is on the website. It's hosted on researcher.org. There is also the ICSE handler in Twitter. By now, it was being used by ICSE 2023, but from tomorrow onwards, it will be our turn to keep news coming up. So something that's already happening, and I'm only highlighting this from the research track because it's something new this year, is that there are dual deadlines. So one of the deadlines that has already, it's happening now. Papers are being reviewed, and there will be another round in August, or starting in August. So this is something new, and that's why we are just highlighting and calling out that this is new this year. Okay, just a second. All right, so this is the map of Lisbon. There are, of course, many things that you can see. We will be over there, CCD. For those of you that have been to Lisbon, is by this tower, close to the river. There is a big conference center there, and that's where we will go. The airport is actually, the airport in Lisbon is quite downtown. The airport is over here. There is metro, and you will be able to go downtown. And downtown is this place where you have multiple things there. Some fun facts about Portugal. The capital of Portugal is one of the oldest cities in the Western Europe. I'm not going to read all this text. You can read it yourself. Portugal is also one of the oldest nation states in Europe. Actually, the borders hasn't changed since the 12th century. And that's, in Europe, there are wars and stuff like that, as it is happening these days. But Portugal managed to keep the borders almost since the very beginning. And Portuguese is one of the official languages of 9 countries. We are not the country where most Portuguese-speaking people live. That's Brazil. But anyways, there are many places where Portuguese can be spoken. In the old days, some people say that we shouldn't be that proud about this, but Portugal owned half of the New World, right? let's not really go into this. This is too much politics. In 1755, there was a major earthquake that destroyed downtown Lisbon. And what we will see is that the buildings downtown are actually not that old. So if you visit other cities like Porto, that is more like older cities, older buildings and stuff like that. But because of this major earthquake in 1755, the downtown Lisbon is kind of new, right? Now, for the braves, the brave folks, you can go like 1 hour north, and you can try to surf the 100 feet waves, like this crazy American does, Garrett McNamara. This is pretty impressive to see. There are tours. I'm not going to organize, or we are not going to organize the tour, the ICSE tour, to surf the big wave, but there are tours to do these things, and if you are brave enough, you can surf it. It's pretty impressive to see anyways. So just a couple of other things. One of the oldest universities in Europe is actually in Coimbra. Coimbra is a city between Porto and Lisbon, like 1.5 hours north of Lisbon. If you go there and if you plan to visit the country, I really recommend to go to the library of the university. It's really beautiful and old, and it's really cool actually. You should try to go there. Now, in Lisbon, there is this, the Bertrand bookstore, and it's one of the oldest bookstores in the world, and it's still functioning. You can visit. It's also really cool to go there and see, the library. Okay, so, when we talk about Lisbon, typically you show a picture of a bridge that looks like the Golden Gate Bridge. I decided to show another one, and this one is a newer bridge from 1998, and it's actually the longest bridge. It's almost 7 kilometers long. It's the longest bridge in Europe. And finally, Portugal is, as you can imagine, Europe's most westerly point. You can also go there. It's actually nice, and it's a cool place. I mean, it's very windy there, but it's a nice environment. And to conclude, we have like just a short video about Lisbon. All right, so this is it. We know that the stakes are very high, especially after yesterday's party. We'll try to live up to the expectation, and you are very welcome in Lisbon. Thank you.
Hopefully another slide will come up. All right. So I'm Lori Williams, as the slide said. It's been my honor over the past 4 years to be the steering committee chair, and my last task as steering committee chair is the closing ceremony. And so we thank very much Yuriy and Anna for taking on the monstrous job of putting together ICSE next year. So thank you so much. And just as a little overview of the ICSEs to come. So ICSE 2025 will be in Ottawa. As you may have heard, ICSE is moving earlier in the year, so in April, so April 26th, so shift back about a month. Tim Lethbridge and Lionel are helping out with that as the general chairs. And then in 2026, magically, okay, here we go. All right. will be in Rio, and Marcos and Rafael will be hosting us there and putting that together. And then finally, what you may not have heard is 2027, ICSE will be in Dublin. Yay! And Brian Fitzgerald will be helping out with that one. And again, many thanks to all the organizing committees of all those conferences. And we put out a wanted ad in 2028. We're looking for a North America host. And the way we've been doing it over the past 5 years or 4 years is that in the fall, if you're interested in hosting, then you put a proposal in. Ari will be the next steering committee chairs, we'll talk. So you put a proposal in for hosting. So, you can start thinking about that over the next few months if you would like to do that. And then the final task is to thank the person who thanked everyone else, John Grundy. I mean, he has just done a magical job of organizing ICSE 2023 and just, been out there, just solid and peaceful and just getting everything done without looking nervous at all. So, and just, organizing all of that, what he talked about. He organized all of the organizers. And it's been a tremendous experience for all of us. So I'd like to have John come up and we can thank John with the plaque. Very, very small token of appreciation. We'll also, at this time, call up the PC chairs to come up and get plaques as well. So Lori and Max. All right. Many, many, many thanks to these three and the thousands of volunteers, as John has said. All right. So my last job is to officially turn the ICSE Steering Committee chairness over to Ari. And I'll be looking, I really feel very confident passing it over to Ari. I know he'll do great things and lots of great things will be happening to ICSE in the future. So come on, Ari.
Thank you very much. So, ICSE is a community-driven series of events in software engineering, and I really look forward to working with all of you to keep this event as successful as it has been in the past 4 years. And for the preceding period, let's give a warm round of applause for Lori, who did a great job as steering committee chair in the past 4 years. Thank you so much. And this closes ICSE 2023. Thank you all very, very much, and safe travels home. Thank you.